Welcome to Open ELMS Podcast, turning your learning into a conversation.
So excited to be here. Today we're diving into something we all rely on but rarely think about, how our medicines get to us safely, the world of pharmaceutical distribution.
Exactly. And the first, and maybe most critical point, is temperature. It's not just about keeping things cool. We're talking about extreme precision.
Right, because a few degrees off can ruin the medicine, right? I see those temperature ranges on the packaging sometimes.
It can render it completely useless or even harmful. Think about it. Standard vaccines need to be kept between 2 and 8 degrees Celsius. That's a tiny window.
Okay, a refrigerator, I can picture that, but what about the newer stuff? The mRNA vaccines, for example.
That's where it gets wild. They need to be stored as low as minus 70 degrees Celsius.
Minus 70? That is unbelievably cold, colder than a polar winter. How do you even manage that?
It's a massive logistical challenge. And then you have the other end of the spectrum, what's called controlled room temperature, or CRT, which is usually between 20 and 30 degrees Celsius.
Which sounds easy, but this brings us to the next big problem, doesn't it? The last mile of delivery.
The absolute riskiest part of the journey. Your medication has traveled thousands of miles perfectly, and then it gets to your front door.
And gets left in the mailbox. I never thought about how hot a simple mailbox can get.
Think about a standard black metal mailbox sitting in direct sunlight. It's an oven. The internal temperature can reach 50 degrees Celsius.
50. That's way over the 30-degree limit for most room temperature meds. So a medicine like insulin, for example, could be completely ruined just sitting there for a few hours.
It could lose its potency so fast. It's a huge safety risk, which is why the packaging technology is so incredibly important.
So let's talk about that tech. How do they fight back against that heat? What's the secret?
It's a 1-2 punch. Insulation and coolants. The insulated container is the shield. It's designed to slow down heat from getting in.
Okay, the shield. I like that analogy. And the coolant is the air conditioner inside?
Perfect. The coolant actively absorbs any heat that does sneak past the shield. The effectiveness of that shield is measured by its R value.
R value. I've heard that for home insulation. So a higher R value means a better shield.
Precisely. It signifies better resistance to heat flow. And the materials we use are fascinating. You have the common ones, like expanded polystyrene, which everyone knows as styrofoam.
Right, lightweight, pretty cheap, but maybe not the best.
It's good, with an R value of about 4 per inch. But then you have polyurethane, or PUR, which is the heavy hitter. It boasts an R value between 6 and 7, much better performance.
But I have to ask, styrofoam and polyurethane, aren't they, terrible for the environment?
That's the major drawback. They are not naturally biodegradable. They stick around for centuries and break down into harmful microplastics. It's a huge problem.
So the industry must be looking for alternatives, right?
Absolutely. There's a huge push right now towards sustainable, bio-based insulation materials. It's a top priority.
Okay, so we have the container. What about the coolants inside? It's not just regular ice, is it?
Sometimes it is. Standard ice packs are great for that 2 to 8 degree range. But for colder temps, they use gel packs with special formulations that can get down to around minus 18 Celsius.
And for that minus 70 degree stuff, we have to talk about dry ice, don't we?
We do. Dry ice is a game changer, but it's also classified as a hazardous material for very good reasons.
Hazardous how? I mean, besides being super cold.
Well, the cold itself is a huge risk. Direct contact with bare skin causes immediate frostbite, a cold burn. You must use insulated gloves.
Yikes. Okay, so gloves on. What else?
The bigger danger is the gas. Dry ice doesn't melt. It sublimates. It turns directly into carbon dioxide gas. In a confined space, that CO2 displaces oxygen, and that can be fatal.
Wow, so ventilation is absolutely mandatory.
It is non-negotiable, and this leads to a crucial design feature. You can never hermetically seal a container with dry ice inside.
Wait, why not? Wouldn't you want it sealed tight to keep the cold in?
You'd think so, but as that CO2 gas is released, the pressure builds and builds and builds until the container explodes.
It explodes. Okay, so the packages need a vent. That's a detail I would have never ever considered.
It's life or death engineering, and it's not just about explosions. This brings us to our final point, structural integrity.
Right, because these packages get thrown around. They're on trucks, planes, conveyor belts. They take a beating.
Exactly. The container can have the best R value in the world, but if it cracks under pressure or from a drop, it's all over.
Because a crack would let the outside air rush in.
We call it a thermal leak, and it can be catastrophic. A small fracture can ruin an entire shipment of life-saving vaccines in a matter of minutes. The temperature spike is that fast.
So the materials have to be tested for impact resistance just as much as for their insulation properties. It's a balancing act between being strong and being a good insulator.
It's the total package. From managing extreme temperatures and surviving the last-mile heat to choosing the right insulation and handling hazardous materials like dry ice safely, all while making sure the box itself doesn't break.
It is so much more complex than I ever imagined. The science behind getting a simple prescription to your door is just incredible.
It truly is a marvel of modern logistics and material science. It ensures the medicine we rely on is safe and effective when it reaches us. Well, that's all the time we have for today. Thank you for tuning in, and we'll see you next time.
See you next time.